Hey everybody, and welcome to our next video in Unit 2, which is all about Lewis dot structures. Now, Chem 1, we all drew Lewis dot structures. However, we are taking this a step further because what fun would it be if we had to draw easy Lewis dot structures for AP, right? We're going to draw more complex Lewis dot structures. And there's a method to do this. So we're just going to go through about 1.5 pages today. We're going to do these few examples and we'll talk about odd electron models. But let's get to it. Let's draw some Lewis dot structures for slightly more complex structures. Let's do the first example here, so A, and we'll work through the steps together. So draw the Lewis dot structure for the following compounds. First steps is to add up all of the valence electrons in the structure. So let's take a look here. I have phosphorus. Now phosphorus has 5 valence electrons, and chlorine has 7, but there's 5 of them, right? So I'm going to take 7 electrons, I'm going to times that by 5. I have 35. Now, that's 35 electrons just from the chlorines. So if I add the 5 valence electrons from phosphorus, that means I have 40 total electrons that I have to place in this structure. So this particular guy doesn't have a positive or a negative charge, so I could skip A and B up here. Number 2 says draw the skeleton structure. So your least electronegative atom is usually in the center of the molecule. So least electronegative happens to be phosphorus. It's a little bit farther away from fluorine. And I am going to connect all of my chlorines to this phosphorus right here in the middle. So I'm just going to draw some chlorines, 5 of them coming off the structure, like this. It's going to be hard for me to do it on here, but we'll see how good I can do it with this pad. Every bond accounts for 2 electrons, right? Because you have 1 electron from phosphorus being shared and another from chlorine being shared. So we have to keep track of all of our electrons here. So let's count up how many electrons are in these 5 bonds. So there's 2, 4, 6, 8, 10. So if I have 40 electrons, I'm going to subtract 10. I still have 30 more electrons I have to put in this Lewis dot structure, okay? If I look at step 3, it says all lone pairs until outer or add, that should say add lone pairs. So change this in your book here. Add lone pairs. Until all outer atoms satisfy the octet rule. So let's go ahead and make sure our chlorines all satisfy the octet rule. And you might recall chlorine should have 3 lone pairs. So let's make sure we start counting because hopefully we get up to 30. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Look at that. At this point, this is the correct structure for phosphorus pentachloride. You might be like, wait a minute. This goes against everything we've done, right? We're going to talk a little bit more about that in the next video. So how do we know that this is the correct structure? Okay, so for now, we're just going to draw some Lewis dot structures. Let's use this same approach for SF6. So sulfur has 6 electrons and fluorine has 7, but there are 6 of them. So 7 times 6 is 42. And I'm going to add these 6 from sulfur, and I have 48. So SF6, we have 48 valence electrons we have to account for. So step 1 is done in this case. This is still neutral, so I don't have to worry about adding or subtracting. Draw the skeleton structure. Least electronegative is always going to go in the middle. So I'm going to draw sulfur in the middle. And I'm going to start tacking on some fluorines here. And there's 6 of them. And it doesn't really matter how you draw it right now. But there we go. Let's count up these bonds. So remember, we have to make sure we have 48 electrons that are represented. So I have 48 minus 1, 2, 3, 4, 5, 6. There's 6 bonds. If each bond holds 2 electrons, that's 12. I'm left with 36 electrons. Okay. Step 3 says add your lone pairs until your outer atoms satisfy the octet rule. Just like chlorine, fluorine has to have 3 lone pairs. So let's add some lone pairs here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Perfect. There is my correct Lewis dot structure for sulfur hexafluoride. Let's try this one. So I have ClF3. So let's count up those total number of valence electrons. Each of these have 7. Chlorine and fluorine have 7 valence electrons. So we could just do 7 times 4 because there's 4 elements total. So that gives us 28. So I have 28 electrons I have to put in my Lewis dot structure. Least electronegative goes in the middle. So in this case, actually chlorine is going to go in the center. And I'm going to bond those 3 fluorines to chlorine. And I have 28 electrons. So remember, let's keep track of all those. 28 minus 1, 2, 3, 2 each, so that's 6, gives me 22 electrons. Step 3, add lone pairs until the outer atoms satisfy the octet rule. So fluorine's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yikes. Okay, so it looks like I have 4 electrons that still need to be placed somewhere in this structure. In this case, we do have to utilize step 4. Step 4 is saying if additional electrons remain, place lone pairs, on the central atom. So if I have 4 electrons that I have to place, that must mean that I have 2 lone pairs on chlorine. And that takes care of those other 4 electrons. It's always good to keep a tabulated list of your electrons like this. This is literally what I do. These here, and I put a little check mark off when I'm done, just so we know to keep track of everything. So let's try the next one, xenon trioxide. So xenon has 8 valence electrons. So there's 8 electrons, and oxygen has 6. So if there's 3 of them, 6 electrons times 3 gives me 18 plus 8 means that there are 26 electrons that we have to account for. So least electronegative, we're going to put xenon in the middle. And let's tack on our oxygens. 1, 2, 3. So I have 26 electrons to place, and 3 bonds means I have 6 electrons. That gives me 20 left. Okay. Here's where a little bit of wisdom starts to come into play. Oxygen always wants to bond 2 times. So in order for oxygen to satisfy its octet rule, we have to remember that it has to bond twice each. So in that case, there's another 6 electrons, which gives us 14 that are left. And then we can go ahead and tack on our lone pairs to our oxygens. So we know oxygen has 2 lone pairs each. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Minus 12 gives us 2 electrons left. The leftovers are going to go on the central atom. There we go. Oxygen is always going to bond 2 times. And once we get into the next video, which deals with formal charge, you'll see why. But for now, just know oxygen is always going to bond 2 times. It has 2 lone pairs. Let's try the next one, radon dichloride. So count up your electrons. Radon's got 8, and chlorine has 7. But there's 2 of them, so that means there's 14. 14 plus 8 gives us 22 electrons. Least electronegative is going to be radon. Radon goes in the middle. And let's tack on some chlorines. Let's keep track of those electrons. I have 22 minus 4 gives me 18. Still got 18 left to place on here. Let's satisfy the octet rule for those outer ones. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Means I have 6 electrons left. So in this case, how many lone pairs does radon have on it? It's going to have 3 lone pairs. There's 1, there's 2, there's 3. There is our completed structure for this molecule. And what we'll talk about in a later video is what's the shape of these, right? Because as you see, we are clearly not working with just those 5 basic shapes anymore. We got some other shapes in there. So we'll account for those soon. Let's try this one, OPCl3. So I have 3 chlorines, 7 electrons each, 7 valence electrons each, 21 electrons there. Let's add a phosphorus, which has 5 valence electrons, and an oxygen, which has 6. So I have 32 electrons to place in this particular molecule. Least electronegative is going to be phosphorus. So we're going to put phosphorus in the middle. And let's just tack on all of our others that surround it. So I'll put an oxygen here. And I'll put some chlorines around the perimeter. And let's start counting up what we have here. So 32 minus 8 is going to give me 24 electrons. Like we said, we know oxygen's always got to bond 2 times. So there's another 2. And let's make sure all of our outer electrons or all of our outer atoms satisfy the octet rule. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. There is our complete Lewis dot structure for OPCl3. Here's an interesting one. So in this case, we actually have a charge on here. And if we look up here, it does say underneath 1, if the molecule has a negative charge, you want to add electrons, of course, because that means I have more electrons than protons. So let's go ahead and count your number of electrons here first. Iodine has 7 and chlorine has 7. So we have 7 valence electrons times 5 gives us 35. But I do have an additional electron because this overall structure has a charge of -1. So I have 36 electrons to place here. Least electronegative is iodine. I'm going to put that in the middle. And let's attach our chlorines around the perimeter. So there's 36 minus 2, 4, 6, 8. Gives me 28 electrons to put. Let's add some lone pairs. Fill up these outer ones first. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Got 4 electrons left. Where do they go? They're going to go on the middle. That means iodine must have 2 lone pairs. Now, when I have a structure that has an overall negative charge, what we tend to do is we write this in brackets. and we show that this guy has a charge of -1 by writing that on the outside. And that just means that that whole structure's got an overall charge of -1. There's our correct Lewis dot structure. And let's try the last one. So ClF2, got halogens here again. 3 halogens, each with 7 valence electrons. So 7 times 3 is 21. But in this case, I have a +1 charge. So that means that I have 1 less electron than protons. So this structure is only going to have 20 electrons in it. I'm going to draw this guy down here. So least electronegative goes in the middle. That's chlorine. Tack on those fluorines. 1, 2, 3, 4. Got 16 electrons to place. Let's fill up these outsides. 2, 4, 6, 8, 10, 12. Running out of room on the page here. Oh, there we go. Got 4 electrons to place. Guess how many lone pairs chlorine has? 2. So this whole structure, like we said, has a charge of +1. So you just write that structure in brackets and you put that little +1 on the outside to show that. You might be like, wait a minute, since when does chlorine not have six valence electrons that are shown? So you might be thinking, okay, so since when does chlorine not have 3 lone pairs? We're getting into some different territory here, right? So we're going to talk about that as we progress through this unit. So don't worry about that just yet, right? It's going to be in one of these. I think it's in the next video, actually. But there are your Lewis dot structures, right? So as long as you follow this particular setup right here, and you got to keep track of those electrons by counting them. If you can count those electrons and follow the rules, like we said, like with oxygen, it's always going to have a double bond, or at least 2 bonds. You should be good. Sometimes, however, I just wanted to show you this. You could have an odd electron model. So sometimes molecules may contain an odd number of electrons. In these cases, the atom with the lower electronegativity does not satisfy the octet rule. So let's consider nitric oxide. Nitrogen's got 5 electrons and oxygen has 6. So that means we have 11 to place. Nitrogen, oxygen. We've already discussed that oxygen's always going to have a double bond, right? And 2 lone pairs. So let's see. 11 minus 1, 2, 3, 4 from the bonds gives us a total of 7 electrons. 1, 2, 3, 4. Minus another 4 gives me 3 electrons. Uh-oh, I got 3 left. Those 3 are going to have to go on nitrogen. And one of those is in a pair, and one of them is not. And that electron without the pair is interesting. But the reason why that particular nitrogen is missing an electron over oxygen is because oxygen is more electronegative. Because it's more electronegative, it's going to make sure it has all of its electrons before nitrogen does. So in this case, nitrogen has the lower electronegativity, which I'm just going to abbreviate to just that, which means that it can have 7 valence electrons over oxygen. So because oxygen is more electronegative, it makes sure it has all of its electrons before nitrogen does. Same thing goes for here. Now this structure is a little bit different. So in this case, I have a little weird thing going on, but I'm going to show you this. Just draw this Lewis dot structure out for you, because oxygen doesn't follow the rules here for reasons we'll talk about in the next video. There it is. So nitrogen's got 5, each oxygen has 6, so that's 12 plus the 5 gives me 17. And this, in fact, should have 17 electrons. Let's double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So same thing goes for here. Because this nitrogen has a lower electronegativity than oxygen, it has the ability to have only one electron, so an odd electron there. And that's because it doesn't want its electrons as much as oxygen does because it has a lower electronegativity. I'm not sure if you're going to see that. This might have been on like an old AP exam, but I like to put it on there just in case you do see it. Always put that last electron on your lower electronegative element if it's an odd electron model. And some elements, of course, we know don't even satisfy the octet rule at all. So something like boron, right? Oops, well, it doesn't matter. I could highlight it. Boron only bonds 3 times, right? So even though we say, okay, it's got to satisfy the octet rule, even hydrogen, right? Hydrogen doesn't technically satisfy the octet rule, but it has a full outer shell. So, or when it bonds, it has a full outer shell. Hydrogen wants to bond one more time to have a full first outer shell of 2 electrons. Boron only has 3 valence electrons. Only has 3 valence electrons, and therefore can only bond 3 times. So you're going to see that sometimes elements don't necessarily follow the octet rule, not because they don't want to, but because they can't. Boron can only bond 3 times, so it's never going to want 4 bonds to it, or to have lone pairs on top of bonds to satisfy the octet rule. This is a little different. We're getting a little funky here. We're taking that Chem 1 knowledge a little bit further. We're going to practice with this in class. So, of course, if you have any questions, please don't hesitate to ask me. We're all in this together, right? So ask me in class next time you see me. Biggest thing, like I said, keep track, right? You got to keep track of those electrons there by drawing that structure out. Follow this set of rules, follow these steps, and you should usually get the correct Lewis dot structure. But again, it takes some wisdom as well to put these structures together. I will see you in the next video, which will be all about formal charge and resonance. So I'll see you then. Bye.